When many of us think of Albert Einstein, images like these come to mind. But to understand the man who wrote the theory of special relativity, we need to look younger. Oh, not that young. The image we get is often a caricature, based off what Einstein looked like in the 1940s and 50s, when many of his theories started to be proven. But Einstein, when he wrote his special theory of relativity in 1905, looked something more like this. And this is the man who we should think of when we think of special relativity. This is what Einstein looked like during his most productive years. So what exactly is this theory of special relativity? Well, it makes two bold proclamations. First off, it says that light is special and that all observers in constant motion relative to somebody else will see exactly the same speed for light in a vacuum. Secondly, it says nobody can perform any experiment to show any difference in physical phenomena when they are traveling at constant speed relative to somebody else. Allow me to explain. Imagine for a moment that there's a train rushing by, and one of the cars you can see through. As you look in, you notice a man is throwing a ball. Now, to the observer from outside of the train, the ball is traveling at the speed of the train plus the velocity that the man threw it at. But to the man on the train, the ball is only traveling at the speed relative to him. However, if the man aboard the train shines a flashlight, both he and the observer outside of the train would calculate the speed of the light to be exactly the same. The reason? Light travels at the maximum speed possible, the speed of light. Light clocks. What is a light clock? A light clock is a light source which emits a light pulse, which hits a mirror and is reflected back down and detected by a detector. When set up properly, it will take exactly 1 second for the light to go from the source to the detector. Half a second to the mirror and half a second back. Now imagine an astronaut in space. He has a light clock set up. The walls of the capsule he's in are made out of glass, and an observer on Earth can use a telescope or some other measurement tool to actually view this. Now, to the astronaut in the capsule, as you can see at the top of the screen, the light seems to just simply go up and down. But to the observer on Earth, the capsule's speed rotating around the Earth makes the light appear to go much further than it does to the astronaut. In the space of 1 second, instead of only going the minimal distance which the astronaut sees, it goes from the left side to the middle, and then after another second to the right of the screen, going a much further distance, a horizontal distance, that the astronaut aboard the capsule does not see. Here's a different way to think about it. Imagine a man is juggling a ball aboard an airplane. To an observer on the ground, the ball is traveling not only the distance up and down, but also the distance horizontally as the plane is traveling from left to right. But to the man aboard the plane, the ball is simply going up and down. This effect is called time dilation. The classic example of it, though, would be the case of the twins. Imagine that there are two twins, born at exactly the same time, as most twins are. One twin decides to become an astronaut, and at the age of 25, he blasts off. He travels at 75% of the speed of light, hypothetically, of course. And he's gone for what seems to him to be only 5 years. When he returns, though, his twin brother is far older than him, almost 80 years old. The reason? Time dilation. Another key idea in the theory of special relativity is the notion of length contraction. In order to measure the length of an object moving relative to you, it is necessary for you to get the two endpoints of the object measured at exactly the same time. If you are sloppy and measure the front endpoint of the moving object before the rear endpoint, then the rear of the object will have moved ahead before you get it measured. This can make all of your numbers come off wrong. This effect makes the objects that move faster appear to be smaller. Look at this illustration. A passing rocket ship is going at 10% of the speed of light. Notice its size. Now, voila, the passing rocket ship is now going by at 87% of the speed of light. Notice how it looks much smaller. Now the spaceship is going at 99% of the speed of light. Look how skinny it is now. Note that the vertical height of the spaceship is unchanging in all three illustrations. Now here's where it all really gets tricky, with Bell's spaceship paradox. Imagine that there are two spaceships, and both pilots have their clocks synchronized at exactly the same time. They both are at a complete standstill with a rope tied between them, or a cable. Now, assuming that this cable is not made out of rubber and is able to stretch a great distance, if both spaceships were to increase their speed at the same exact rate and reach the same exact speed, would the rope break or not? Well, according to Bell's spaceship paradox, it would. And here's why. While two observers on both the lead ship and the following ship, the distance may appear to be the same, but as they increase their velocity, the distance between them will at first slack. The distance between the two ships will be actually shorter. And as you notice, at the higher speeds, they start to pull apart. Given enough time and enough of an increase in velocity, the rope will break. Because even though the distance may appear to be the same between the objects, and they are even moving at the same speed, the distance between them will slightly warp over time. So to kind of put this all back together, think about it this way. As the Earth rotates, you yourself are traveling at a certain speed. But that's not the only speed that you are undergoing. The Earth is also speeding around the Sun. And the Sun is only one part of a tiny section of our Milky Way galaxy. And it is speeding around the Milky Way galaxy. And our Milky Way galaxy is only one part of the local group. And the local group is speeding away from the event of the Big Bang. And all of these factors are pressing on us. And we're traveling at hundreds of thousands of miles per second. But we don't even recognize it. To us, it's all relative. Relative how? Relative like your great Aunt Susan? No, not that kind of relative. Relative in terms of when we measure how fast something is moving, we don't judge it in terms of its absolute speed. We judge it based on its relative speed and how fast it seems to be moving without counting in all of these other forces that are playing in on it. If you're on the train and you throw the ball across the room, you measure the speed you perceive it at, not at its absolute speed, which is what the observer outside would see it as. And when you're traveling at faster speeds, time moves slower for you because you span greater distances in the same amount of time you normally would. So, for instance, the twins, this affected time dilation. This is all explained by this. And from someone observing this object that's moving at 75% of the speed of light, it would seem much contracted compared to what it would look like at a standstill. So it's relative in terms of what object you're looking at and who is observing it. The brilliance of all this is that before Einstein came up with this theory, a theory that may seem perfectly normal to you now that the theory has been so widely accepted. Before Einstein, there was this whole theory that the Earth was passing through an ether that no one could really understand, but it only made sense in terms of how light was reacting. There was also this notion that Earth was a special case in the universe, that physics acted differently in our region of space than it did elsewhere. But this theory of special relativity, it pretty much says, hey, the laws that are true here are true in all inertial frames of reference. If it's here or if it's elsewhere, physics reacts the same. In other words, there are no privileged inertial frames of reference. Furthermore, it sets that the speed of light in a vacuum is independent of the motion of the light source. So even if a star is moving away from us or moving towards us, the light it emits can only travel at a certain speed. The speed of the light itself, that's constant. And that is groundbreaking. Thank you, Einstein.